Excuse me. So here we have a problem that says at a given point above Earth's surface, the acceleration due to gravity is 6.5 meters per second square. And it says, what is the altitude of this point from the center of Earth? Okay. And it wants us to express answers in terms of Earth's radius r. All right. So let's go ahead and give you a visual here. Here's planet Earth. Here is an altitude h, not drawn to scale, whatever h is. But all that it says is that at this particular height above the surface, the acceleration due to gravity is 6.5 meters per second square. Okay. I do want to point out, however, the problem asks us for this altitude from the center of the Earth. So it's important as you practice, you read the questions and you read the statement, what is it that it wants? So here I notice right away it says from the center of the Earth, right? It didn't say from the surface of the Earth. So please distinguish between phrases from the surface versus from the center. So because it says from the center, I'm going to make sure I draw out what it wants me to find. So this red line that just came up, this is the distance that it wants me to find because it says from the center of the planet. Had it said from the surface of the Earth, I would just find h, but it didn't. It says from the center. All right, so read carefully. In order to find this d, I'm just going to set up my little chart here. My reference point will be my surface once again. Acceleration due to gravity is capital G times m Earth divided by the radius of Earth square. All right. And because it wants us to find d, I need to set up what the function is for this particular height measured from the center of the Earth. Well, I will use the same function, but here I chose to use the subscript altitude just to indicate that at this particular height above the surface, it is 6.5 meters per second squared. The numerator stays the same because to find the acceleration due to gravity at any point is capital G times the mass of the planet. In this case, is mass of the Earth. But here in the denominator, I replace r with just d. D being the center the distance from the center all the way to where this particular problem references at some height above the surface. Okay. So ultimately, I'm trying to find d, not h, because d is measured from the center. I can just substitute that for d in my function. But the next thing I hope you notice here is that you have a couple of variables that are the same on both the left side and the right side of the chart. So I noticed that g and me are both constants in this particular problem, right? The numerator in the left side is the same as the numerator on the right side. So that's going to trigger me to find gme, the function for it. So in order to isolate for gme, I can just multiply both sides by r squared for this left side where it says surface. To get gm by itself, multiply both sides by r squared. Hence, r squared gets moved up to the left numerator. So it's gr squared, which is equal to gme. But I notice, again, the numerator on the right side of the equal sign here is also the same. So in order to get that by itself, I will multiply both sides by d squared. So same algebra step. So therefore, I have a statement that says, excuse me, g at some altitude times the distance from the center square is equal to big G times me. Well, at this point, I have two statements that represent g, me. So what I want to do is I want to set the two functions equal to each other, right? Because they both represents capital G and me. But once I do that, it's easy to find d because, well, I know what g is at the surface of the planet. That's 9.8. It doesn't want us to find a numerical answer. It wants us to express our answer in terms of r. So I want to keep r as a variable, right? G altitude here is given at 6.5. So really, I'm just going to do algebra first before I plug in numbers. I'm going to get d squared by itself because ultimately we're trying to find d. So algebraically speaking, to get d squared by itself, I need to divide both sides by g altitude. Okay. So therefore, I have a statement that says g at the surface of the planet times the radius of the planet divided by acceleration due to gravity at some altitude, h here. That's equal to d squared. Well, here we can just plug values in. G at the surface of the planet is 9.8. R is kept as R because it wants it in terms of R. G altitude is given as 6.5. So if you plug in 9.8 divided by 6.5, you get 1.51. Well, I'm going to carry the r squared down because I haven't done anything to that yet, right? All I did was I simplified these two values or these two coefficients on top and bottom. So 9.8 divided by 6.5 is 1.51. That's r squared. But you notice that we still have d squared. So therefore, to get d by itself, we would square root both sides. Therefore, the square root of 1.51 is 1.23. The square root of r squared is simply just r. And then, of course, the square root of d squared is just d. So our final answer is going to be 1.23 r. And so the distance from the center to the surface, wherever this altitude is going to be a distance of 1.23 r. All right, and that's it. Say no, don't be back.